Okay, so we're going to look at another related rates problem here. So this is kind of a classic related rates problem. Probably any calculus book you look at will have a similar problem to it, just slightly different numbers or different variation on the same theme. All right, so we've got several different things going on here. We probably need a diagram for this, and we also want to make a list of our variables and rates, things that change. All right, so I'm going to do kind of both of those at the same time. Variables and rates, and we'll make a diagram over here so that we can label what those things are. All right, so we've got a street light mounted at the top of a pole. So there's the light mounted at the top of a pole, and that pole is 20 feet tall. So before I label things with numbers, I might make sure I read through the problem that the height of that pole is not changing. It's not. There are other things changing in the problem. And then we've got a 6-foot man standing near the street light on level ground. So we'll draw the ground here. We've got a right angle in there. So a triangle here. We've got a little person standing over here, not to scale. Okay, so there's the person. He's walking away from the light, and shadow formed by the street light is getting longer. So let's draw in a little shadow here for him. So there's his shadow. And as he walks away, his shadow is going to get longer. So it asks us how fast is the length of the shadow changing when he's 5 feet from the pole and walking away at 3 feet per second. All right, so we've got a couple different variables here. The man is 6 feet tall. I'm going to go ahead and label that here as 6 feet tall. And I've got two different distances that are changing here. One is the distance from the man to the pole. So we could use d for distance, but with the derivatives, we use that dt notation a lot. So I'm just going to put here a w since he's walking away from that pole. And then he's got a shadow length. And so I've got really two variables here. And we're asked to figure out how, when one of them changes, how the other one's changing. All right, so my variables are his distance from the pole to where that man is. And so we're given some information about a rate of change there, and shadow length, and asked about that. Okay, so this problem is a pretty typical problem. There's one other little thing that you have to pay attention to in this problem and recognize is happening in order to get an equation that's going to relate our variables here. And that is that when a shadow is cast by a light, probably should try to draw this so it looks straight. When a shadow is cast by a light, it's because that's where that shadow hits the edge of the person here. Oh, I drew my shadow a little too long. We'll shorten that up. All right, so I've got some triangles going on here. And in fact, I actually have two triangles. And because these two triangles share some angles, they are similar triangles. So I have one big triangle here formed by the pole and this entire distance here along the ground, which maybe we could label as W plus S. And then I have a smaller triangle formed by the man that fits inside that larger triangle here. So the man that's 6 feet tall. All right, so we've got to kind of recognize that there's this triangle relationship. That's the key that makes this problem work. I'm going to go over here, though, and label my variables and my rates so that when I take all those derivatives, I'm ready to just plug things in and find what I need to find. All right, so as he walks away from the light, his shadow is getting longer. How fast is the length of his shadow changing? So that's what we need to find. When he is 5 feet from the pole, so that's the W distance here. Be careful not to keep that as constant. I do have some things that are constant in this problem, but this is not one of them, how far he is from the pole. When he is 5 feet from the pole and he's walking away at 3 feet per second. So that W is changing at a rate of 3 feet per second. I need to pay attention to whether that's a positive 3 or a negative 3. So I want to think about whether this W is getting bigger or getting smaller. It's walking away from the pole, so W is getting bigger. So that's a positive 3 feet per second with my rate of change. And we're not given information here about S. We could maybe find that if we need to. We may or may not need it when we solve the problem. Okay, so then the other thing is setting up an equation that relates the variables from the problem. So here's where you have to use a little geometry and recognize that you have these two triangles that fit inside each other. So both of them right triangles. They share this angle here in the corner. So these are similar triangles, which means that their sides are always in the same proportion to each other. So there are several ways to set up that proportion. Here's how I would think about it. For this bigger triangle, I've got this side that's 20, and then the other leg here that would be W plus S. So 20 to W plus S is going to be equal to those same sides, corresponding sides on the smaller triangle, so 6 to S. So there's my proportion. So 20 over W plus S equals 6 over S. All right, and I'm going to need to take some derivatives. I could take some derivatives with it written in that form, although the derivatives are going to be a little harder than they might be if I rearrange this equation a little bit before I take some appropriate derivatives so I can plug in my related rates. So since I have a proportion here, I would probably go ahead and cross multiply to simplify that. So I'll have 20S equals 6 times W plus S. Again, I could take a derivative now and plug in things after I do that, or I can continue simplifying. I might notice that if I distribute on the right side, I'll have some S terms on both sides of the equation, and I could move those so that they're on the same side of the equation to simplify this equation a little bit before I find those derivatives. Okay, so 20S equals 6W plus 6S, and then I'm going to subtract 6S from both sides. So I'll have 14S equals 6W. Okay, I could continue doing more algebra if I want, but at this point it's a pretty simple equation. So I'm going to go ahead and differentiate both sides with respect to t. All right, so on the left side, the derivative of 14s is just 14. Remember that we're differentiating with respect to t, though. We've got these rates of change. So 14 times ds dt equals, and then on the right side, we've got 6. The derivative of 6w is 6, and then times dw dt. Okay, so I'm now ready to find the information that I need. So the ds dt is what I'm going to find, so I don't have anything to plug in for that. The dw dt, I need to plug in 3. Notice here that we didn't actually end up using this 5 that's over here. Sometimes that happens, that you don't use these values for the variables, but anything that you're given about rates of change, you should be using all of those rates of change when you plug into your equation here. All right, so when I rewrite that, I'll have 14 ds dt equals 18, 6 times 3, and I'll just write that over here. And then I need to solve for ds dt. So you can divide through by 14, you'll get 14 over 18, or if you reduce that, you'll have 9/7. So 9/7 does not come out nice as a decimal. I'll write that over here. ds dt is 9/7. That doesn't come out nice as a decimal, so I'd probably just leave it in that form. You could write that as 1 2/7. If you want to write it as a decimal, you're going to have to round, so you end up with an approximate answer instead of an actual answer. And then I should label my answer here. The rates of change on this would be in whatever the units of S are. So the shadow is measured in feet, and whatever the units of time are. So that's measured in second. So this would be in feet per second. And that is a positive rate of change. S is getting longer, which it told us in the problem, but kind of just a way to make sure that your answer makes sense.